Hi, I'm Kevin Dorma. Welcome back to my whiteboard. So I've done a few videos on energy efficiency and power generation. And what we've looked at is a typical power generating facility is about 30% efficient. Now if it's a combined cycle gas turbine, it might be around 50%, but we're still ditching a lot of waste heat, or a lot of our valuable heat as waste heat. So how do we make it more efficient? Well, it's apparent that we need to use the waste heat. We have to utilize that somehow to make the whole process more efficient. So let's take a look at how we can do that. And to examine this, we're going to flip the problem around and we're going to use our need for waste heat as an opportunity to generate electricity very efficiently. So let's take a look at this. We'll consider that we have a small manufacturing plant where we need 3,600 kilograms an hour of relatively low pressure steam. We'll say it's 200 kPa gauge and it's saturated. So this might be a food processing facility. Now, we need a boiler to make the steam. Okay, so we could build a boiler, design a boiler to generate steam at 200 kPa gauge, and that would be the way that we provide heat. But we could do this a little differently. We could produce the steam at a higher pressure, and then from that, generate power, like this. We could have a turbine, attached to a generator, make some electricity, steam goes in, low pressure steam goes out. So here we generate high pressure, superheated steam. We'll drop it through a turbine, spin the turbine, make electricity, and as the outlet, we get saturated steam. So let's crunch through the numbers quickly and see if this makes sense for our small plant. To figure out whether this makes sense, we need to do some design calculations. And the place to start with the steam power plant is with a Mollier chart, which is a graph of enthalpy versus entropy. So I've got the Mollier diagram in front of me, and let's zoom in and plot a few points and come up with a reasonable design. So I'll just zoom in a bit. Yeah, that's enough. Okay, so our inlet is our outlet. We're producing steam at 200 kPa gauge, so that's 3 bar absolute. So that's right about here. So I'm going to put a circle there. So we'll drop a circle right here. Whoops, that didn't work. So that's at 3 bar right there. Okay. And we'll just make a note of what that enthalpy is. That is H2, and we're going to say that that's about, according to my notes, 2720 kilojoules per kilogram. Okay. Now our steam turbine is isentropic. We'll assume it's isentropic or 100% efficient to start with. Let's draw the isentropic line. So we're going to draw a line from here, and we're going to draw it straight up. There. That's the path that our steam will follow as it goes through the turbine. So it can come in at any of these conditions. So let's say it's 425 kPa gauge and whatever that pressure is, and the steam will drop through the turbine and give us energy. First thing we need to figure out is how high a pressure do we think we can get away with? Well, the one thing that I know is for a 150 class flange, which would be for a low pressure steam system, the limit is 275 Celsius and about 1100 kPa. So that would put us right about here. That would only leave us with a few hundred kilojoules per kilogram of energy that we could add to the superheated steam, and honestly, I don't get out of bed for a few hundred kilojoules per kilogram, particularly on a small system. So let's make this worth our while. Let's use a 300 class piping system, and let's make some decent steam. So for 300 class, the absolute max is 425 Celsius at about 2900 kPa. So 425 Celsius is about that line. And 2900 kPa will follow that down here. About there. That's the absolute max that we can do. So we're going to take our design point to be somewhat lower than that. So we're going to put a circle right here. And we'll drop that down. Right there, that will be our steam inlet point. And that one, H1, is equal to, according to my notes, 3,240 kilojoules per kilogram. So that means we will make steam at 2,500 kPa and 400 Celsius. Now we can go back to our whiteboard and do some math. Okay, so back to the whiteboard, and let's write down the things that we know. We'll make the steam at 2,500 kPa. And at a temperature of 400 degrees. And at these conditions, the enthalpy was 3,240. The outlet conditions have an enthalpy of 2,720. And that means the enthalpy difference for an isentropic process would be 520 kilojoules per kilogram. Since our mass flow is very conveniently 1 kilogram per second, this says that the amount of power that we could make, if the world were perfect and we had a perfect 100% efficient isentropic turbine, we could make 520 kilowatts. But the world isn't perfect, so we're not going to make 520 kilowatts. But for a turbine of this size, we might be able to get away with 50% efficiency. So let's suppose our turbine is 50% efficient. That means our power is 260. So we're going to make 260 kilowatts of power. And that's actually quite a bit. Next, we'll look at the cash flow that comes with this, and we'll look at the capital costs. For the cash flow analysis, we'll look at the value that comes with making 260 kilowatts worth of power, and we'll look at the additional gas that we need to consume. And for this boiler, it's probably 85% efficient. So we'll keep that in mind. So does it make sense? So for the electricity, the cost of electricity for my house here now in Calgary is 12 cents a kilowatt, 12 cents per kilowatt hour. And this comes out to That's 0.12 cents per kilowatt hour times 260 kilowatts times 86. I will say it's 8,500 hours per year. And we go through the math, and what we get is $265,000 per year in electricity that we've made. Okay, so how much additional gas did we consume? Well, that's equal to, and again, the cost of gas for my house, straight from my electricity bill, is $8.50 a gigajoule. And we multiply that by 260 kilowatts. We'll divide that by our efficiency of 0.85. And we'll get the number of hours per year, and we get 8,500 hours per year. And for this, we get about $80,000 per year in gas that we consumed. So we consumed $80,000 of gas, and we made $265,000 worth of electricity. So economically, that's really good. Environmentally, that's also really good, because the efficiency that we created the electricity at was 85% versus the absolute very best combined cycle gas turbine, which only does about 50. So this is really good. The difference between these two, the cash flow, about $186,000 per year. Okay, so that means $186,000 per year. And largely it's due to a decreased consumption of electricity. I'm assuming that whatever we make, we can consume. So it decreased our electricity bill by a large amount. That makes me happy. I like decreasing expenses. Now, as far as the capital cost goes, what's this thing worth? Well, I don't have any costs for power generator, but I know what a motor is worth. And I know that a 260 kilowatt motor is about $140,000. And I know that a steam turbine is about half the cost of a motor. So this is about $70,000. So the total should be about $230,000 for the equipment purchase. That means the total installed cost, using an install factor of 2, should be about $460,000. Okay, so we got $460,000 that we have to spend, and we're going to save $186,000 per year. So our payback looks like it's in the range of about 2.25 years. And for doing literally 15 minutes worth of engineering, that definitely says we should spend a little bit more effort looking into this, because this looks like a really good project to do. So, if you have a small facility and you need some reasonably large amount, like 3,600 kilograms an hour of low pressure steam, it can make sense to generate the steam at a higher pressure, make power through a turbine and provide your power. Because the amount of energy that you make, the electricity that you make, is done very efficiently, and it will decrease your utility expenses, and it looks like it will have a pretty good payback. That's all. Thanks for watching. Take care. Bye.